Thank you very much. This talk is all about water and machine learning. So let's start with the water and then dive into the machine learning.
I'm so glad I parked at the front today. That's coming fast. Should we move our cars out front of the building and just go? Like, it's not going to take much.
Yeah, but look at these ones here, they're all moving. Even if they came now, they still can get their car.
No! Oh, no. Yeah. Oh! Oh my goodness!
Water can be a fairly violent and destructive natural force. And although heavy storms happen regularly, we are nonetheless each time surprised when it's getting dangerous. And it's raining not only on mountaintops and forests, but also on streets and roofs. To protect our infrastructure, we must be able to deal with this kind of water masses. And that in particular in the rare and extreme cases. These are the cases that take place like once every 30 or 100 years. On roofs like these, it rains up to 500 liters per second. That's about 200 bathtubs dumped every minute. And nonetheless, the water level must not rise above 10 centimeters, otherwise it gets too heavy and the roof may collapse. So to get this kind of water masses off the roof safely and reliably, we need on one hand a carefully designed piping system and on the other hand a hydraulic trick. Negative pressure is the basis of modern roof drainage systems. Using negative pressure, the water is literally suctioned off the roof, such that the dangerous water masses cannot accumulate on the roof in the first place. And it works like this. By carefully choosing the diameters of the pipes fully fill up during heavy rain. Thus we end up with a closed water column, yielding in a negative pressure, suctioning off the water off the roof like a vacuum cleaner. And thanks to the special choice of the diameters, we also get a high flow velocity inside the pipes. Thus the pipes cannot clog anymore, and essentially we end up with a self-cleaning system. Traditional roof drainage systems need a slope. That's on one hand, they need a lot of space and it's fairly difficult and complex to build. Modern roof drainage systems based on negative pressure do not have this drawback anymore. So let's make an example. On this roof here with roughly 7,000 square meters, we get about 200 liters per second. To get the right dimensions, that is the dimensions to which we end up with the closed water column suctioning off the water off the roof, we need a software system that suggests the dimension and also evaluates the hydraulics. With ProPlanner, Geberit is offering this type of software, so let's plan this building in ProPlanner. I prepared the building a little bit here. In our user interface, it's a schematic. Here, these are the pipes, these are the outlets, that's where the water enters the system, and these are the ground connection, that's where the water leaves the system again. We can easily add some pipe. We place an outlet, and of course we also have to define the length of the pipe, maybe 10 meters. And then we start the calculation. We now get for each pipe a suggested dimension, which we see here. So like for each pipe we get a row and a suggested dimension as well as the hydraulics inside this pipe. So this one is fine, we have 200 liters, we reach 187, that's within that visible range, that's okay. Here we have the second pipe, and here we have a problem. We have a negative pressure, which is below 800 millibars. That means the negative pressure is so strong that under heavy rain, the pipe will collapse. The pipe has this diameter, and it will look like a giant fist squeezing together the pipe like this. Thus the water will not be able to flow through anymore, and it stays on the roof. And the software is not able to find a better solution. So now I, as an end user, have to guess a better solution. Here, that's the point where I need all my hydraulics knowledge, my expertise, and in particular my gut feeling to guess. So I guess a better, maybe, I guess another dimension, maybe it's better or not, we will see. I guess and we restart the calculation. Now the problem changed. It's down here. And again. And you see where this ends. I have to go on and go on until eventually I may find a suitable solution to build this building. If I would build the piping system nonetheless without finding a good solution, then it might get really dangerous. We already saw that the pipes may collapse. If they collapse, the water stays on the roof and the roof collapses as well. In the case the roof does not collapse yet, then the pipes may clog later on, resulting again in water on the roof and the roof collapses. If the roof still resists, then the water spills over the sides of the building, damaging the facade. So this is really not a good idea. And it is difficult to find the right dimensions. Until today, there's no algorithm, no feasible algorithm that guarantees to find a solution when there exists one. What's comparatively easy is doing the hydraulic simulation and test if it's an admissible system. So we end up with a situation that we only get heuristic algorithms. These are algorithms which have to implement best practices and do their best guessing, and maybe they succeed and maybe they don't, as we've just seen before. And that's, of course, the entry point for our machine learning solution. Because using machine learning, we now want to complement the existing algorithms, thereby improving the success rate. And, of course, we integrated that in the software you just saw before, and then it looks like this. So I undo the manual changes I did before, and now start a new calculation using the optimizer. We call it optimizer, but that's our machine learning-based solution. It just takes a little bit longer from an end user point of view, but otherwise the end user does not see any difference, except that it gets a perfectly calculated piping system, which we now can build and enter the system, enter the building safely. So the basis of this machine learning solution was the following two observations. First, the end user draws the geometry of the system and starts the calculation. And in 75% of the cases we are lucky and we're done. Otherwise we have to enter this vicious loop of trying and guessing the dimensions. Experienced end users, they don't guess the dimensions on arbitrary pipes, but they always start at the two pipes between the transition of the horizontal and the vertical. These are kind of the neuralgic pipes, the ones with the strongest impact on the hydraulics. That's the first observation. The second one is the end users, they just look at the hydraulic list. So essentially they take the hydraulic list as input and then they predict the dimensions as output. So we kind of have a mapping. And using machine learning we want to approximate this map. We collected over a period of roughly 2 years data to train the models. And now we have 3 models, 2 based on neural networks and 1 on a support vector machine, which is now integrated into the system. And then we end up with the following new setup. The user does the planning, starts the calculation, and if the traditional algorithms fail, we do not show anything to the end user. But we use the output of the hydraulic list as input to the model. with all the data, all the errors, all the messages, and then let the model predict new diameters for the neuralgic pipes. Then in the background, we simulate the end user changing the dimensions and start a traditional algorithm again. So now let's take a closer look at the implementation side. And of course, sorry, that's the most important part, of course. Our success rate increased from the 76 to the 93%. From an implementation point of view, we were fairly restricted in the choice of our machine learning platform. We are a team of only 5 members, and we are normal software developers. We do software and we do testing. Thus, for us, it was never an option to build up our own machine learning infrastructure. But Gebrit is already using Azure, that's the Microsoft Cloud, for quite a long time. And part of Azure is Azure Machine Learning, which is a fully cloud-based solution. And that was fantastic for us, because the way it is designed, we don't need any locally installed software, neither on the developer machine nor on the client side. Just we need an HTTP connection. And everything else, like from data wrangling to model training to operating the web service, is done using the web browser. So in the next few minutes, I would like to show you how we can train a model using our regional data, train a model to predict these dimensions, then deploy it as a web service and test it. Since everything happens in the browser, we switch to the browser. First, we create a new document. So this is a graphical UI where we drag and drop some elements and plug them together, and that's how we design our model and our web service. Everything starts with the data. As a preparation, I uploaded our CSV with our dataset in here. And we can take a first look at our dataset. Here we see we have 12,000 columns, 12,000 rows and 1,600 columns. Each row represents a unique building which was built or planned during the last 2.5 years. So like the first row represents a building from Poland. When I click on the header of a column, I do get some summary statistics on all values, as well as a little histogram down here. So the label column contains the value of the neuralgic pipe which we want to predict. And then here on the right hand side, we have all the other columns containing the hydraulics list you just saw before. So like the full 2-dimensional list, we squeeze together in this one row. So like the length of the first pipe in this building was 5 meters. And now our task is to build a model which takes these 1,600 columns and predicts the value of the label column. Of course, we not only want to predict the model, to get a model, but we also want to test it, as we saw in the talk before. And to this end, we first split the data set. To this end, we have an element called splitter, which we place, plug them together, and we choose now a ratio of 80% for our model training. So on this part, we will have 80% of the data, here the other 20. Then we proceed to model training. And we choose the trainer element. We plug in our data set, the 80%, and now of course we have to tell the trainer which column contains the value to predict. In our case, that was the column called label. And now here's the final choice in our model. Which kind of algorithm do we want to use? So we have a classification problem. And there are a number of different algorithms to choose from. Like from decision trees to neural networks to even support vector machines down here. For this example, let's choose the neural network. And we plug it in again. Here on the right-hand side, you see the Hibder parameters of the neural network. Currently, it's just one layer by default, just having 100 neurons, but that's fine for the time being. So when we let it run, we get down here our trained model. And to test it, we have to apply the trained model to our test data set. The process is called scoring, and of course there's an element. We plug in the model, and we plug in the data set. Here as an output, we will get a copy of our input, of our test data set, together with one additional column, the one containing the predicted value. But of course that would be now annoying to just test all these 2,000 rows, so we would like to get like a summary statistic of our success rate. For this, that's our final element. We choose evaluate. And let it run. And we're done. Now again, using visualize, we can take a look at the statistics. And the first number contains our success rate. So in 57% of the cases, our model made the correct prediction, the same one as the one that we had in our label. If you are interested in more detail on the success rates depending on each dimension, we get here a matrix. For example, here in this row, this row represents all rows where the label was 90. So in 59% of the cases, the model predicted 90 as well, in 23, one dimension too low, and in 12, one dimension too high. So like on the diagonal, we have the success rate for each dimension separately. But now let's assume that we are satisfied with our model and we're ready to deploy it for production. So here's a little magic button. I will press it, the matching will happen, and then we will take a look at what happened. Here's what was going on. First, we got a new element which contains our stored model. Like all requests in production will run against this model. That's the one we just trained. Then the two blue elements here represent the input definition and the output definition. It's like the JSON schema. So as input, we expect the same data as we had in our CSV. That's essentially 1600 properties as a JSON. And as an output, again, we get the 1600 properties plus one, the one we predicted. But of course, it's fairly annoying. I don't want to have the 1600 properties in my output. I'm just interested in that one only predicted value. So let's drop the other properties. To this end, there's an element called column selection. And again, we plug them together. And we have to make the choice of our property which we want to have. I only want to have one, and this one is the one with the prediction. And now let's check if everything is fine. Once we deploy the service, we will get a stateless REST-based web service using getting JSONs as input and JSONs as output, and we will communicate with it using HTTP post requests. And we're ready to deploy. So now that we have our web service in place, we can test it using this little UI. So let's assume, again, we want to get a prediction for the market Poland. And here now we can enter all the 1600 values which we would generate using our traditional algorithms. I won't fill that in, it's just like we want to see that we do get some answer. So we send a request to the service, and here we get the response. this part here, is actually the JSON that was contained in the body of the response of our post request. And here you see the 56, that's the predicted dimension. Here on top you see the credentials that we have to send with each request. And here that's the URL where we have to send the request to, which was generated. And so that we don't have to write the client on our own, or that we get a little test client, the C-generated implementations, one in C#, Python and R, where we just have to plug in our credentials and then send our requests. So it's fairly easy, fairly low barrier to start and run with your own models. So if you now have the impression that everything was very easy and no problems, that's great. Of course, it was my intention. But nonetheless, we also had some difficulties and obstacles which we had to deal with. And I would like to share some of them with you. The first problem was that the training time took too long. Training speed was too low. Over a period of roughly 2 years, we collected 2.5 million calculations. And when we started to train our models with them, it took about several hours or even a day. That was too long for us. So when we took a closer look at our data set, we noticed that our users tend to send the same calculation several times. On average, they send it 4 times for each system. So in reality, we just have 600,000 real different calculations. And then a closer look showed us that in these 600,000, our users like to do little changes on the system. So like increasing the length of a pipe a little bit or decreasing it a little bit. But nothing that really changes the hydraulics of the system. So we end up with only 150,000 really different buildings. Out of these, we already know that we are able to calculate about 75%. So we end up with only 35,000 difficult buildings for which we want to find a good solution for our roof drainage calculation. And now here's a crucial question. Should we train with the 35,000, the small data set, or should we use the large data set? And what's the impact on the accuracy? And to our relief, it turned out that the impact is low. It's only about a decrease of the accuracy of 1%. So we used the small data set for training. However, finding the small data set was fairly strenuous, because it took about 20 machines running for more than a month to really distill these out of this huge pile of data. So now we were faster, but our model did not get any better. And that was our second problem. Our success rate was too low. Like in our first go, we just saw a success rate of 57%. And all we did, we always remained in the range of 60+%, so we didn't really get better. So we thought, okay, let's take more data. Because more data means more training, means hopefully a better model. And that's where the lightning strikes. Because we don't need like 10% more data, we need something like more like 10 times more or 100 times more. But there's simply no big data in the small world of roof drainage systems. Because the number of newly constructed large buildings is fairly limited. These are buildings like airports, like shopping malls, or like football stadiums. Even if you take the full world into account. And we do have about 7,500 clients in more than 42 countries. And only if a new building is planned, we do get new data to train. And waiting for 10 years was not really an option. So, surprisingly enough for us, to the rescue came speech recognition. Because we learned that in speech recognition they have a very similar problem. They need huge data sets to train their models. But the amount of audio files containing the spoken text is fairly limited. So they used the following approach. They took their audio files and mixed in some noise. So they mixed in some traffic noise or like some people talking in the background. Essentially changing the input a little bit. And then they used the newly generated files to train the data, their models. And we tried to do the same. So we took our existing models and we randomly changed them a little bit. Changing the length of some randomly chosen pipes, increasing, decreasing, stuff like that. That's like shaking the building a little bit. And the big advantage of this is you can shake as often as you like, and each time you get a new building. So now we have an automatism to generate new data. And we generated about 500,000 new buildings and trained our model with it. And it was absolutely fantastic. We had success rates of about 85%. So we were dancing on the tables. However, the party was abruptly over when we started to test our newly trained model with newly built buildings. Because then our success rate collapsed back to the 60%. That was bad. And of course we were wondering what happened. And I guess the following thing happened. Because the difference between the newly generated data and the one which we started with was so small, then there was not a lot to learn from this difference. So our new model did not contain really new stuff. And that's why the success rate collapsed. And also because, like, we used the original data set for testing, our original data set was not independent anymore from our generated data set. So our test set was dirty. And that's like if you go and take a test that you already know the questions in advance, maybe up to some random choices in the phrasing. So that was bad luck. And we were stuck. So we needed a new approach. And that approach was again in the data and in the following observation. Our traditional algorithms, they already predict the dimension. And the true dimension, the one which we want, was often very close to the one predicted by the traditional algorithms. That means in 90% of the cases, they were in the range of plus minus 1. So instead of predicting 1 out of 10 dimensions, we changed our problem to predicting just the direction of change, taking as a starting point the output of our traditional calculation. And that increased the success rate to 72%. So that was great. And now that we increased the success rate, maybe we can repeat that success. And again, so continuously increasing our success rate. That was our goal. So let's see if that's feasible. So our current setup is we have a model with an accuracy of 72%, yielding a system with an end-to-end success rate of 93%. Now, if we had more data, then we should get a better model. Or even if we had a better algorithm, or even if we had perfect data, a perfectly large data set, and a perfect model, what would be the impact on the end-to-end success rate? And we simulated that. And it turned out then that the simulation just showed us that we get an increase of only 1%. So waiting for 10 years wouldn't have been a good idea, just to get 1% more. So now it's fairly difficult to improve anymore. But there's one little thing we still could do. Because our data set, the labels, are given by our end users. And our end users are humans, and humans make mistakes. Now, let's get one step further and think about what would happen if we had a perfectly labeled data set. That's like a data set where some friendly alien in the neighborhood would give us the data. So like whenever we have a building and we want to predict, and the building has a successful solution, then in our data set we have the correct label. So that's like machine learning experts' paradise. We assume we have a perfect model, we assume we have an arbitrary large data set, and we assume that our data set is perfect. What would now be the end-to-end success rate? And it turned out, yes, it would be helpful to have an alien, but only by 1% more. So that's about the level where we can get to. However, these simulations also give us some hint and some insight into what we have to do if we want to crack this 95%. because it tells us that as long as we stay in the original machine learning part, that is trying to get more data, trying to get a better model, trying to get better data, will not help anymore. So what we need, we have to change the setup end to end. Maybe we have to find an algorithm or a new approach predicting different dimensions and not only neuralgic ones. Maybe we have to use something else like an iterative approach, not doing it in one go, something along these lines. So in a sense, like having a very good idea now would be stronger than having an alien as a friend. So that's also in a sense comforting. So where are we now? We just saw that finding the right dimensions for a roof-drainage system is fairly difficult. And up to now, there's no feasible algorithm that guarantees to find a solution. Using machine learning, we were able to increase the success rate of the traditional algorithms from 76 to 93%. And that's a huge advantage for our end users. Because in a sense, in the old times, the end users had the time to build up a good gut feeling and a good intuition over a period of years. Nowadays, our users just have a few months until they do some job rotation and do something else. So they really do need a better calculation. For us, also interesting was that our team structure shaped our solution. Because we are not machine learning experts, we were in a sense condemned to find a tool set and an infrastructure which is easy to use. And even like when we started, we were not even able to do an evaluation of the machine learning platforms because we didn't know what to look for. So there we took a risk, but we also had to address this risk using architectural measures. So in the sense that we were able to substitute our machine learning infrastructure at an arbitrary point in time in the future. So once that we had our now easy to use tools, that was fine, it was no problem to do the training. But nonetheless, we encountered different obstacles and problems, which we just saw some of them before. For us, the most interesting one was that, or the most interesting result was that waiting for more data would probably improve our model a little bit, but not that much. And we don't have that big of a data set. And as of today, we not only have the machine learning part as a web service, which we use from our client side, but we have the full calculation as a REST-based web service in the cloud. And we're using it not only for our own software, but we're also offering it to other software vendors. So in case you happen to be a software engineer in the sanitary software development space, please let us know. We will gladly open up this service for you as well. Thank you very much.